Have you ever wondered if the world around you is real? Does that chair you're sitting on, or the screen you're looking at, still exist when you turn away? These might sound like questions from a late-night philosophical debate, but they are at the very heart of one of the most mind-bending experiments in all of science, the Double Slit Experiment. This single experiment, so simple in its design, shatters our everyday understanding of reality. It suggests that the universe might be far stranger, more mysterious, and more connected to our consciousness than we could ever imagine. Prepare to have your perception of existence fundamentally challenged. Let's begin with something familiar. Imagine you have a wall with two vertical slits in it. If you were to throw a handful of tiny pellets at this wall, some would bounce off, but some would pass through the slits and hit a backboard behind it. You would expect to see two distinct lines on the backboard, corresponding to the two slits the pellets pass through. This is exactly what happens. It's common sense. The pellets behave like tiny, solid objects, following predictable paths. Now let's switch from pellets to waves. Imagine you're in a pool, and you create ripples on the surface of the water. When these water waves encounter a barrier with two slits, something different happens. The waves pass through both slits simultaneously, and on the other side, the new waves from each slit interfere with each other. Where the crest of one wave meets the crest of another, they combine to make a bigger wave. Where a crest meets a trough, they cancel each other out. This creates a distinctive pattern on the backboard, not of two simple lines, but of many lines. This is called an interference pattern, showing areas of high and low intensity, a hallmark signature of wave behavior. So far, so good. Pellets act like particles and waves act like waves. Now let's step into the quantum realm, where things get bizarre. Scientists decided to repeat this experiment, but this time with the fundamental building blocks of our universe, electrons. Electrons are tiny bits of matter, so you would naturally expect them to behave like the tiny pellets, creating two simple lines on the backboard. But that's not what happened. When scientists fired electrons one by one at the double slits, something astonishing occurred. Over time, as more and more individual electrons hit the backboard, they didn't form two lines. Instead, they built up that classic interference pattern, the one we only see with waves. This is profoundly strange. How could individual particles, fired one at a time, create a pattern that suggests they are interfering with each other? It's as if each single electron somehow passed through both slits at the same time. It's behaving like a wave and then interfered with itself before landing on the backboard as a single point. Think about that for a moment. A single particle, a fundamental unit of matter, seemed to be in two places at once. It was not a particle or a wave. It was both existing in a state of potential, a probability wave that described all its possible locations until it finally chose one upon hitting the detector screen. This dual nature, known as wave-particle duality, is a cornerstone of quantum mechanics. The scientists, as baffled as we are, decided they had to find out what was going on. They wanted to know which slit each electron was actually going through. To do this, they placed a tiny detector, like a microscopic camera, next to one of the slits to observe the electrons as they pass by. They reasoned that, by watching, they could finally solve the mystery. They would see each electron go through either the left slit or the right slit, and then it would hit the backboard. They expected the interference pattern to remain, just with the added knowledge of each electron's path. But the universe had an even bigger surprise in store. The moment they turned on the detector to watch the electrons, the interference pattern vanished completely. Instead, the electrons started behaving exactly like the tiny pellets from the first example, forming two distinct lines on the backboard. It's almost impossible to overstate how revolutionary this discovery was. The very act of observing the electrons, of measuring which path they took, forced them to choose a single path. By looking, the scientists had collapsed the wave of possibility into a single definite particle. Let that sink in. The behavior of the electron changed simply because it was being watched. When no one was looking, it acted like a wave, existing in a superposition of all possible states and going through both slits at once. But when an observer was present, it behaved like a particle, choosing one definite path. This leads to the profound and unsettling question that titles this exploration. Does reality exist when you aren't looking? The double slit experiment suggests that at the quantum level, things do not have definite properties until they are measured or observed. An electron isn't at a specific location until we look for it. Before observation, it exists only as a cloud of probability. This idea challenges our most basic assumptions about the world. We tend to believe that the moon is still there, even when we're not looking at it. But quantum mechanics tells us that, for the fundamental particles that make up the moon, their properties aren't fixed until they interact with something, until they are observed. What does it mean to observe? It doesn't necessarily require a conscious human being. In physics, an observation, or measurement, is any interaction that reveals information about the system. The detector at the slit